So I started talking about a particle immersed in a solvent, a rigid particle of radius r of a mass m, a spherical particle immersed in a solvent. And then the solvent molecules are bombarding this particle in random directions and some random values. The solvent molecule is coming and hitting this. And for this, we wrote down very straightforward Newton's equation, that is a mass times acceleration dv at time t by dt, right? And then there is a friction coefficient, zeta vt. And then the force is coming from the solvent molecules, which we wrote down to be random force. So this is a random force. This is friction. This is the inertia. We are still talking about single particle. And I told you last time that unlike the Newton's problem, where this F is a constant force, therefore this equation is a deterministic equation. Instead of that, what we have in reality is a random force. If it's a random force at a particular time, its value is always changing. Suppose I take the magnitude of F as a function of time, the magnitude of that would be highly fluctuating, like that, very quickly, like that. This is F as a function of time. This is plus, minus, 0. Well, magnitude means the amplitude. It could be negative value also, right? Or you can say this is in one direction. Instead of putting the, I can say F along one direction, for example, X component. Highly fluctuating. Therefore, if I want to solve the velocity for this equation, I cannot do that because depending upon what time I'm going to want to solve this problem. So if I look at somewhere here at that time, the value of F is that, then I'll have one solution. And if I'm somewhere here, the value of F is something different, I'll have different solution. So that is not deterministic. So the way we solve an equation of this type is in terms of some averages, only in a statistical sense. So this equation is called a Langevin equation. Right? This is an example of a stochastic equation instead of a deterministic equation. You know, everything is fixed, everything is known, right? Precisely described, then that will be called a deterministic equation, and you know how to solve those equations. So here it says stochastic equation. So if F is random, then V will also be random. V is also random. Right? This is also So how are we going to describe this? So if I want to look at this velocity, for example, it again one component, right? But I'll write it like this. As a function of time, this is time, it is going to be fluctuating something like this. Etc. And when you take this instantaneous velocity as a function of time, and then if I average it out, I can get some average value. That average value will be something like this. Let's say the average value is like that. So this would be average V at time t. In general, I'm not putting any scale here. I'm not putting plus, minus over it. In general, there would be an average velocity, which I put as an angular symbol, 2 brackets. And the questions then are, how much fluctuation we have, right? What is amplitude? Amplitude of fluctuation, right? And of course, the average, I already told you, I want to know the average value, and I want to know the amplitude of the fluctuation. Amplitude of the fluctuation, I want to know that. Then what I also want to know is whether there is any correlation. And in fact, the way I have cartooned, the velocity is correlated in the near neighborhood. Suppose I have a velocity value here, and I'm looking at a time which is very short, then that velocity is correlated with that velocity. But on the other hand, if I go to a long time, for example, say somewhere here, the velocity here is not correlated with this. If I go here, for example, the velocity is very different. The velocity at a longer time is not correlated. So there is some correlation time for the velocities. So this is something that we want to understand. Correlations. Okay. What are the correlations? Now, let me take one step at a time. I think I began to introduce this the other day. So if I look at any average quantity, in this case, let me take V average. How do I define V average? What I do is I measure the velocity at this point, everywhere over a period of time. So I measure V at some, say, T1, say even T, some T, I measure this. And then I start measuring this at some time, T0. I start at an earlier time. So I measure this from T0, right? And then I integrate over this dVt over dt up to a final time with a delay of, say, tau. So my clock starts at this point, say that is at T0. Then I wait for tau, measure, keep on measuring here. And then I come from T0 plus a tau, right? And then I average over this duration. And then I want to do this measurement in the limit of tau going to be a very large number. That means I'm able to average over a long period of time. Particularly when you do simulations, this is the way you construct averages. You should construct averages by doing the simulation long enough and then average over many periods. Then you get an average. You see, here is, for example, right? This seems to be correlated here. So there seems to be some period of these fluctuations, correlation time of these fluctuations. So you have to run the simulation for very long enough times, and then you have to average it over that duration. In simulations, usually it comes naturally. In simulation, things happen so quickly, and then you make measurements over very long time anyway. Therefore, it's a natural, when you talk about averages in experiments, this is exactly what you are doing in real experiments. In simulations, you have to do similar things. Okay, so how are we going to how are you going to get understanding of these quantities, the amplitude of the fluctuation, correlations? In particular, I'm interested in correlations. For example, I want to know how velocity at this point is correlated velocity at this point, at this temperature. Velocity at this time is correlated with velocity at that time as a function of duration, right? Suppose this is my clock, how long, over a period of time, how does velocity get correlated? That's my target. And we can define that only in an average sense because there is no deterministic way to do this. Okay, so how do we do this? In order to do this, since the right-hand side has the term F, I need to say something about this force, some statistical properties of this force. And the way I have already mentioned is the way I have cartooned here. So they look at the force correlation. There is also similar to this velocity correlation. There is also force is also noisy, but there is some correlation time. Since these solvent molecules are hitting the particles so quickly and so fast, so the fluctuations are at very short time scales. Like when the solvent molecule comes and hits, it's probably like a nanosecond or something like picosecond, nanosecond. So the time in which the force fluctuates is at a very, very short time. On the other hand, a massive particle, a micron diameter colloidal particle or a 20 nanometer polymer chain, the way they are going to move because of these collisions, the correlation time is going to be longer. So instead of this very quick fluctuations in the random force, the velocity is going to be longer. Therefore, I can decouple the statistical property of the random force from the massive particles behavior and use this as an input. So let me assume. I'm going to assume, make certain assumptions to solve the problem with a paper and pencil. So number one, I'm going to say F varies rapidly, right? Varies rapidly in comparison with the particle. The Brownian particle. And then I'm also going to say that F is independent. F is independent of V. The random force, when the solvent molecules hit, they don't care about the particle's velocity, independent of the particle velocity. Okay. V depends on F, but not the other way around. So then, given this, I'm also going to make assumptions that the average of F of t is 0. This is one assumption. The second assumption I'm going to make, right, it turns out that it is not an assumption, it actually becomes a theorem, but I'm going to state it. And in view of the time, we will not be able to make a derivation of this in this course, but this is something you can find in various books. Because I'm interested in correlation, right? So this is the average force, random force is 0. So this is a force correlation function. Force at one time dotted with force at another time. That is force at one time dotted with another time. That one, it turns out to be equal to, for our general situation, 6 times kBt zeta times the delta of t minus t prime. This delta is a delta function. This means when the argument is a 0, it has a value. When the argument is not 0, it has no value. It's 0, right? So that means they are locally correlated. That means that the correlation time in these fluctuations so short, correlation time, that is the force and force, the correlation, the time over which they are, like here for velocity correlation, here they are correlated. I mean, here also there is a correlation, but the time duration where they are correlated is so short, we can imagine that it's a delta function. Okay? Please notice that it depends on this friction term, zeta, and also it depends upon temperature. Right, so here is my friction term, and this is my temperature. Right, temperature is thermal energy, and the friction is a dissipation. Friction costs energy, and this is a fluctuation. Now, this is called a fluctuation dissipation theorem. This statement is called a fluctuation dissipation theorem. The left-hand side is fluctuation, and the right-hand side is a dissipation, and they are equated, and it's a theorem because this is true. This is exact. Right. Now, the input that we made in deriving this expression, I'm not giving you the derivation, but the input, key input that went into this derivation is that in equilibrium, because the average, time average for a long time, right? That's also equilibrium average. In equilibrium, we know from your elementary physics and chemistry courses that kinetic energy, right, half mv squared. Half m is mass, v is at a particular time v squared. In equilibrium, half mv squared is equal to, in 3 dimensions, 3 divided by 2 kBt, right? That is the thermal energy. Kinetic energy is equal to 3 by 2 kT in 3 dimensions. And you know that this is called equipartition theorem, going back to your elementary courses, equipartition theorem. Okay. So this is right. This information is used. This information is used in getting this result, because we want to make sure that it captures equilibrium properties. The noise in the system, the random force in the system must obey the equipartition theorem. This information is used in getting this. If you do that, you get this result. Okay. So we are going to use, you'll see this in textbooks all the time. So I have to give you as a statement at this moment, right? And maybe there will be a problem that you can do later on if you wish, but right now, let's take this as a statement. Now the question then is, we want to get results. So what? So results. And I like to get, my goal is to get, right, V average. What is that? The other goal that I like to have is, as I pointed out, V at t and dotted with V at some 0 time. See, there is some duration. What is that? This is the correlation function. This is velocity correlation function. Okay. And the other thing that I like to do is, I also want to look at the position of this particle, center of mass of the particle at time t minus center of mass of the particle at an earlier time, right? And how does that behave? What is that? How does that behave? And as I'm telling you repeatedly, I cannot, when I write like this, I cannot find the answer, because this is a stochastic problem. That means I have to think in terms of average. Only that is meaningful. Only in an average sense is meaningful. So I can calculate average of this guy, average of that person, that quantity, etc., etc. Right? These are the kind of questions we are going to be looking at. That's what we are going to do. Okay, given that target, let's go ahead and do the work. Okay, the first thing that I want to do is, right, I like to look at the average value of V. That's easy, average value of V, because you know V is proportional to this F, right? This is V here, so V is proportional to F. So when I take the average of this one, since the average of F is equal to 0, average of V will also be 0. We'll prove this a little later, but in principle, right, the average of V is 0 at any time. So first result is Vt is equal to 0. The way you can easily see that is, I saw on your blackboard, when I was listening to your question, on your blackboard, I saw lots of Fourier transforms. So this is a digression. Since I saw on the board in front of you, I'll write down like this, right? The equation goes like right? Going back to the original equation, m dv by dt plus zeta v, that's equal to f. That's the equation we are writing. When you go to the Fourier transform of this, right, I omega m, I saw on your board, I omega m zeta v, and then plus zeta v is equal to f. That means I omega m plus zeta times v is equal to f. That means v is equal to f divided by I omega m plus zeta. So I take the average. V average is equal to f average divided by I omega m plus zeta. And f average is 0. So V average is 0. So that's the proof, for example. Okay. It comes very nicely, right? So if on the right-hand side, f is average of f is 0, average of V will also be 0. So now I like to go and look at this quantity, the second quantity. That's my goal right now. I want to calculate this. And I want to do this exercise. The reason is, if you understand how we do the calculations for one rigid Brownian particle, then we can accept the way we calculate the velocity-velocity correlation function for polymer chains as well. Because the technical mathematical technology is the same, we do not have to do, work it out on a blackboard in a classroom. You can do it in private in your as a homework problem, right? So therefore, I want to show you how we do these things for the Brownian particle, because it's very straightforward. And also it's a very fundamental result, as you are going to see later on. Okay, again, my goal is to solve this equation. Okay, so let me open a new page because I need a long page. Let's do that. So m dv by dt plus zeta v is equal to f. Everything at some time t. That's given. So let me divide this by m. So dv t by dt plus zeta by m vt is equal to f t by m. M is mass, zeta is a friction coefficient. Okay, that's what I have done. And how do we solve this equation? Although this is a stochastic equation, I can write a formal solution for V for a given value of f. Then we can consider averages in the statistical sense. How do we do this? This is a very standard technique. I'm sure you have done many problems of this type, but just for completeness, I'm going to give a solution for this. Okay, so let me define this. Let VTE, okay, I'm not going to put the vectorial signs, you understand, right? These vectorial signs are always there. So VT, let me define this to be equal to e to the minus zeta over mt. This is called integration variable, right? And let me define a function yt. I'm just changing the variable. Vt is written like this. If I write like this, I take the derivative of this. Okay, so dv by dt is equal to, I take the derivative of this, keeping this constant, then keep this constant, take the derivative of this. First time, keep this constant, take the derivative. That gives me minus zeta over m, and then the rest of them, e to the minus zeta over m t yt. That's the first term. I kept it constant, took the derivative of this. Then I keep this constant, take the derivative of that. That would be plus e to the minus zeta t over m and dy t by dt. Okay. Now this is equal to minus zeta over m v, of course. The square bracket is v, right? That's a square bracket, that's v, plus e to the minus zeta t over m dy t by dt. But please notice, here is a dv by dt. And then I have minus zeta over mv. I can bring it to the left-hand side. Therefore, dv by dt plus zeta over mv is the one that I have on the left-hand side. That's the reason why I did this, right? So I bring it here. Therefore, the left-hand side turns out to be, therefore, left-hand side turns out to be e to the minus zeta t by m dy at t by dt is equal to, you know the answer. That's equal to the right-hand side, which is f at t by m. That means dy t by dt is equal to e to the plus zeta t over m f t by m. Okay, I took this to the right-hand side. Now I'm going to integrate it out. Yt from starting from t is equal to 0. The initial velocity of the particle is, say, v0. Okay, initial velocity at t is equal to 0 is v0. Okay, or maybe I'll put in the argument. V0. Let me write it like that. The initial velocity at t is equal to 0 is v0, of course. V0, go back here. When t is equal to 0, v0 is t is equal to 0, e to the 0 is 1, y t is equal to 0. So this is same as y at 0. Okay, so I'm going to integrate this equation dy by dt. That means, say, y at a particular time minus y0, right? I integrate dy, integral of dy, I bring dt to the right-hand side, right? That's going to be dt, let's say dt prime, 0 to t, right? And then I have e to the t now becomes the dummy variable, integration variable, zeta t prime over m, and then f t prime divided by m. Okay. Okay, so that means, and y0, I know that y0 is, this is a v0. I know that. Okay, so therefore, yt is equal to v0, right? Therefore, yt is equal to, y of t is equal to v0 plus 0 to t dt prime e to the zeta over m t prime f t prime divided by m. Now let's go and look at, I'm interested in velocity, right? So I go vt is e to the minus zeta over mt times yt. So multiply both sides by this factor. Okay, that means if I do that, right, I get vt is equal to v0 e to the, I'm multiplying this factor, minus zeta over mt, zeta over mt, that's the first term, plus I have 0 to t dt t prime e to the, I'm multiplying minus zeta over m over t. So e to the minus zeta over m t, and I already have this plus t prime, so I put like this, t minus t prime, minus t prime, and then I have f t prime over m. Okay. So now let's do, given this, so we have an expression for Vt. Now what I'm going to do is, I'm going to multiply it by V0, right? I have an expression for Vt. I take this expression because I'm interested in this quantity. See, I'm interested in this quantity. I have an expression for Vt. I'm going to multiply by V at 0 time on this one. And then eventually I'll take the average. So let's do that. I go to this expression and I multiply it by a V0. Okay, so therefore Vt t dotted with v0, that's equal to v0 square, sorry, v0 square, right? Because I have v0 and multiply v0 again, v0 square times e to the minus zeta over m t. Then I have, right, zeta over t. Then I have this quantity, right? And I'm going to multiply by v0, right? So therefore that turns out to be, let me write down here, plus 0 to t dt prime e to the minus, I'm copying this again, zeta over m t minus a t prime. And then I have v0 and, sorry, v0 dotted with f t prime. Of course, there's an m there. Okay. Then what we do is v0 is some fixed number, right? At the 0 time, I know some velocity, right? Now what I'm going to do is I'm going to do the average. The average, I take the average of this, average of that, average of that. Okay, so Vt dotted with V0 is equal to the equilibrium quantity V0 squared e to the minus zeta over mt plus this term coming from the noise, thermal noise. But now I already told you average of F is 0. So that is, right, average of F is 0. And I also told you that the F is independent of V. Therefore, what happens is this term becomes 0. So I have accomplished my goal, namely V of t. What I wanted to get is V of t, this quantity, V of t dotted with V0, what is that? That is given by this quantity. Okay, so therefore I rewrite V of t correlation function. V0 average is equal to V0 average squared. Okay, so I don't have, if it's a dot product, as you guys know, I don't have to write a vectorial sign. So V0 square average times e to the minus zeta over mt. It's an exponential decay. Okay, now what is V0 square? V0 square average, I already told you that, right? Which is here. Half mv squared in equilibrium, because that's an equilibrium quantity, right? In equilibrium, half mv squared is equal to 3 by 2 kt. Therefore, v squared would be 3 kt divided by m. This factor of 2 cancels with this factor of 2. I bring m downstairs. So v squared in thermal equilibrium would be equal to 3 kBt by m. So therefore, what I have is, this is 3 kBt over m e to the minus zeta over mt, and this is v of t, v of 0 average. Okay, that's our goal. That's what we wanted to get, and we got that. Okay. Now, let me plot this. Okay, I want to plot this. And let me remind you, right? Let me remind you what we had for Newtonian mechanics. If the particle is a Newtonian, right, I showed you this result. I showed you for the no external force, this is Newtonian, going back to previous lectures, right? If I looked at the velocity for a Newtonian particle, no Brownian motion, no stochasticity, the velocity is also the initial velocity times e to the minus zeta over mt, right? It's an exponential decay. But this is for the velocity. Now for our problem, the Einstein's problem of Brownian motion, the average velocity is 0, right? This doesn't exist for us. Average velocity is 0. But on the other hand, if I look at velocity-velocity correlation, that has this behavior. Velocity-velocity correlation looks like this. Okay, now let me plot this. So I take V at t dot V at 0 average divided by Euclid twine correlation function. Instead of t here, I'll put 0 here. V0 dotted V0 average. And that's equal to, of course, e to the minus zeta over m t, and I plot to the left-hand side versus time. This is t, this is this quantity. I'm plotting that. And of course, when t is equal to 0 is 1, and t is equal to infinity is 0, and as you guys know, it's going to fall down like that, exponentially falling down. And then at the value of, say, 1 over e, and so 1, at what time I get 1 over e? When t is equal to m divided by zeta. So what I can do is, right, this is equal to, I could rewrite to be e to the minus t over tau. Right, when t is equal to tau, I get 1 over a. So the correlation function decays to a value of 1 over e at this time tau. And that tau is defined to be, because of this, right? Because of this, that is m divided by zeta. Okay, and this is the correlation time for the velocity fluctuations. That's the correlation time for the fluctuations. That means what? That means for times shorter than tau, they are correlated because this correlation function is significant. For times are longer than this tau, the correlation function is insignificant. They are not correlated. So going back to my cartoon, right? For times shorter than the correlation time, their velocities are going to be correlated. But if I go beyond certain duration, which is given by tau, then they are not correlated. And what is a tau? That tau, right, is precisely m over zeta. So that depends on, the correlation time depends on the mass of the particle, the Brownian particle, and also the friction coefficient of the Brownian particle. Okay, and you can see this, when the friction is too high, the correlation time is going to be short. You can see that, right, physically. So that's the correlation function we have got. Now, if you want to know the correlation time in a problem like this, or in general, any characteristic time scale in any of these problems, you can get that result by inspection of the original equation. Okay, now let me take a small digression and show you physically how you can get. You do not have to go through this whole calculation of these 2 pages to get that correlation time. This is given by inspection, even by looking at this equation, we can tell this equation. Okay, let me rewrite that equation once more as a digression. Write that to be, what is that? That's the dv by dt, right, plus zeta over mv, that's equal to f over m. Please look at the left-hand side, right? I could rewrite this to be again dv by dt plus v divided by m over zeta is equal to f over m. I'm not solving any equation. I'm just rewriting in this way, where the numerator is v, the dimension is velocity, and also the velocity. This is velocity. The denominator, I have time, and then this must be also time, right? Velocity, because they have to, dimension, they have to balance. Velocity divided by time, the velocity divided by time. That time is characteristic of your problem, the way you define the problem. So this better be tau. This is tau. This is a characteristic time of your problem, the way you define this problem. Therefore, you must get that one. When you do mathematics, you must get that result. Okay, and that's what we got. By doing this, it is what we got. Okay, so now what I like to do is, I like to go and answer the next question. Next question is this question. R center of mass of this particle at some time t minus R center of mass at some time 0. All right? Let me do the first, the way we did for Newton. Remember, going back to Newton's calculation. Newton's calculation, what we did was, if you can find it, and in the Newton's calculation, right? So we did the following. See, this is a displacement, R of t minus R of 0. We calculated this. R of t minus R of 0 is this quantity. This is a deterministic problem. And it showed like this. R of t minus R of 0 is going like linear with the time. This is more like a car moving, I told you, and eventually it break, it stops due to the friction and it becomes immobile. That's what I told you, all right? So let me calculate the analog of this for R of t minus R of 0. Let me calculate the analog of this for our Brownian motion problem. Okay, how do we do this? Same way we normally do, right? Which is, let me say, this is R of t is center of mass position of the particle minus R of 0. This is equal to V at, say, t prime, dt prime, and from 0 to t. Right? The displacement is integral of velocity. So let me take the average of this. Take the average of this. This is 0, right? Average of V, this is 0. Therefore, the displacement, average displacement, mean displacement is 0. This is an important result. Please compare this. This is on an average sense, the displacement of the particle is 0. It doesn't go anywhere in an average sense. This is exactly in contrast to ways what I showed you before for Newtonian thing. R of t minus R of 0 is not 0. So this is a scale. It starts from some value to begin with, right? At t is equal to 0, it is 0, then it takes off, and then reaches an asymptotic value of the initial velocity times m over zeta, and it stays put, right? This is mean displacement. There is definitely a displacement. The displacement is given by that number for long times. For short times, it depends upon whether the time is shorter than this characteristic time or longer than characteristic time. Please, at the same time, you notice the characteristic time in this case is also m over zeta, because there is no escape from that. The reason is, even in this particular case, the equation independent of this f, the equation is this. So when I divide by m, dv by dt minus zeta over mbt, and the characteristic time, the denominator would be m over zeta. So the characteristic time is the same given the structure or shape of this equation. All right, so now going back here to our present situation, in contrast to the previous case, this is 0. Now let's say calculate the mean square, R of t minus R of 0 square of this, mean square displacement. Right, let's calculate that. That you can do by using the usual technique, right? Because I already told you R of t is the first integral of V. So what I have is, let me write dt1 from 0 to t, dt2 from 0 to t, right? V at t1 dotted with V at t2 average. Right? Because one integral of dt1, vt1 is one factor of displacement. Another factor of displacement is dt2 dot vt2, right? So that's the mean square displacement. But I do know this quantity because vt1 minus vt2 is we just calculated. vt1 minus v times v0 is this. So vt1 dotted VT2 would be e to the minus zeta over m T1 minus T2, right? And it doesn't matter which way you go, right? Whether I take V T2 times VT1, right? Therefore, it's only time difference, right? I have written T minus 0. That's what happens. So when I make the correlation function here, it's a time difference between these two measured values, right? So I know this expression, substitute that, and it's a very simple integral, right? Because in exponential integrals, you know how to do the exponential integrals. If you do that, the answer turns out to be, they follow it. This is equal to 6 kBt over zeta. This is an exact answer, okay? Times t minus m over zeta. If you do this calculation, m over zeta, 1 minus e to the minus zeta t over m. Please do that. I'm not doing the integral for you. It's a simple integral. If you do that, this is the answer you get. Okay, this is exact, gentle. Now what we have to do is we have to look at the shape of this equation. How does it look like? Okay, let's do different times. Let's do different times. Let me look at a very short time. Oh, maybe I should stop here. I'm sorry, I didn't. Oh, we are running out of time, right? Can we, June Fang, I thought I lost track of time. Shall we stop here? Yeah, I'm sorry. You should have told me. Stop sharing.
Okay.
Okay, let's look at the implications of this exact result for a Brownian particle. In contrast to this deterministic problem of Newtonian dynamics, right? We have average displacement is 0, displacement 0, and a mean square displacement is given by this formula. And let's look at different limits of time. When I say different limits of time, I have to compare with, right? I have to compare with the characteristic time. Remember, m over zeta is tau. So let me look at the time which is shorter than tau. That tau is, of course, m over zeta. We know that. How does that look like? So this is equal to mean square displacement, right? This is mean square displacement, right? What is that? That's equal to, let's take two limits. When t is smaller than tau, right? M over zeta is tau. T is smaller than tau. Let's expand that. Okay, so I have, let me do it here, 6 kBt over zeta. Here t minus m divided by zeta, 1 minus, let's expand that exponential. Okay, e to the, right, 1 minus, right, 1 minus, I have written 1 minus here, I'm writing exponential here. Okay, that's equal to 1 minus zeta over mt plus half zeta over m square t square, etc. That's the way it works. Okay, now let's see this quantity. I have plus 1, I have minus 1 here. So they go away. Then I have negatives times negative, negative times negative, zeta over m times t. Then I have m over zeta, right? M over zeta kills zeta over m. Then I get a plus t, and then I have negative sign. So as a consequence of this, this kills that term for t small when I do the expansion. Therefore, I'm left with this term. That's a leading term. Higher order terms are going to be negligible. And I have zeta over m squared. I have m over zeta, right? So that one factor will go away. Then I have plus sign here, negative sign here, another negative sign here. So we'll get plus, right? And then I have 6 here and 2 here, right? And then therefore what I get is 3 kBT over m, right? And then, right, there is, look at this, 6 kT, there's a factor of 2, they go away 3 kT. And then here, one factor of zeta, right? And then here I have m over zeta. So one factor m over zeta goes away, therefore I have zeta over m, right? And that factor of zeta cancel with the zeta, so I have 3 kBT by m. That's what I have. And then I have t squared, right? Minus times minus plus t squared. This is not a surprise, right? Because this is equal to, as we know, that's equal to v squared average t squared, right? 3 kT by m, I told you, is a v squared. V squared average of 3 kT m. That's the equipotent theorem. There is no, right? V squared is equal to 3 kT by m. So what this does is, for very short times, the particle has not yet seen, for very short time, the particle has not experienced the constant bombardments by the solvents. For extremely short times, compared to the characteristic time, it is ballistic. Mean square displacement goes like a time square. On the other hand, if a t is longer than tau, the characteristic time, which is set by the mass of the particle friction coefficient, if it is longer than that, then what happens is, right, e to the minus t, which is large, argument is large, therefore that is 0. The 1 minus, 0 is 1. And then m over zeta is tau. So this t is larger than tau. Therefore, the whole curly brackets converges to the leading term t. Therefore, I get 6 kBT over zeta t. And then what we call is, we call this kBT zeta divided by zeta, that we call to be d. Therefore, only, this is an important statement, only for long times. What do we mean by long times? That means the t is larger than tau. That tau depends upon your system. Whether it's a Brownian particle, if you have a polymer chain, you'll have a different value of tau. But only for long times, you can have mean square displacement r of t minus r of 0 squared. Mean square displacement is equal to 6 dt. You'll have this is Einstein's law. Okay. Only under those circumstances, you will be able to see. The problem could be stochastic. So if you do computer simulations, for example, you have to wait for a long time to ensure that you get this, because that depends upon this tau. If you are not waiting for long enough, or even in your measurements, if you're not waiting long enough, then you will not see this. You will see some intermediate behavior that is not in the Einstein's regime. When this happens, we call this to be diffusion. In this limit, we call diffusion. The particle undergoes diffusion or Brownian motion. Okay? So I'm going to sketch this formula again to emphasize. So by just looking at the shape of this equation, we could get this result and we could get this result for short times and long times. And I'm going to plot this. I'm going to plot this as a graph. How do we do this? So let me plot R of t minus R of 0 square average, that's important, as a function of time. For short times, I told you that it's going to go like quadratic, right? Because it's a t square. Mean square displacement goes like t square. That is, it's Newtonian, right? This is Newtonian dynamics, ballistic. It goes like t square. Then eventually, for long times, what will happen is, for long times, it will go like linear. Okay. And this is t. Here it goes like t. Here it goes like t square. Okay. Where is a break point? When does it? This is Einsteinian. Okay. This is Einstein. So for a Brownian particle, for very short times it's Newtonian, for long times it's Einsteinian, and the crossover, this is given by the crossover point. Measure of that crossover is given by tau, which in this particular case is m over z. Okay. Now let me take a root mean square displacement. Right? Root mean square displacement, which is R of t minus R of 0 square, average it, and then take the square root of that. This, that is, in the average sense, I'm taking root mean square displacement. That's like a measure of displacement, but the displacement we know, average displacement is 0, but the root mean square displacement is the measure of the spread of this Brownian particles movement as a function of time. And then what will happen is, as you know, for short times, it'll go like t, linear, because square root of t square is t, right? Exactly like the way we saw for the Newtonian problem. In the Newtonian problem, no average here, deterministic, RT minus R0 is linear with the time for early times, and eventually it becomes immobile. It stops at that value. Here, what happens is, in contrast, what happens is this keeps on going. This keeps on going, because now it's the square root of t, right? Square root of t is here. Here it's linear. This is, but in contrast, right? For the Newtonian case, right, there is no averaging. For the Newtonian case, maybe I'll use a different symbol. For the Newtonian case, it's R of t minus R of 0. No averaging, right? There, what you get is you get something like this, and then it becomes immobile. Immobile. Okay? And that's not what we observe. This is Newtonian, deterministic problem. And this one is, of course, this one is Einstein. Okay, this keeps going. And this is what I was trying to share with you experimentally, right? Experimentally, we found and I showed you this, right? Experimentally, Perron found out that the fine particles go, stop, start again, mount, descend, mount again, without in the least tending toward immobility. They are not immobile, they keep on going. Right? They keep on going. This was a Perron's experiment, is direct proof of Einstein's theorem. And then since he knew the trajectories, he could also measure, Perron could also measure, right? Measure the mean square displacement. as a function of time. And he showed, indeed, this was observed. Mean square displacement was proportional to time. While these people are mounting and descending, translationally moving everything, he could verify this Einstein's law. So this is valid, but I want to emphasize again, valid only for long enough times. Okay, now I want to make one technical remark. One technical remark is, okay, I'm telling you everything is an average, right? Only in the average sense. Therefore, we can determine the probability of finding a particle at time t, some position at t, given it had a position at an earlier time. So that probability I can write in general, I can write probability of this particle at some location R compared to its an initial location at R0 after an elapse of time from t. This is equal to, you probably know this already, 4 pi d t in 3 dimensions, 3 divided by 2 e to the minus r minus r0. R minus r0 square divided by 4 dt. Okay, so you could also get exact answer. It's a Gaussian for a Brownian particle. Again, this for long times, for t larger than tau. For long times, that is the distribution function. It's a Gaussian, and you folks know you use this expression for random walk statistics. Remember, we wrote Gaussian statistics probability distribution function of end-to-end distance vector, assuming it's a random walk, right? So that's where that formula comes from. It comes from here, which is a solution of this Brownian particle problem that we discussed here. Okay, so now the question is, what do we do with this? Okay. What's the use of this? Okay, we have described mean square displacement. What can we get out of this? So let's look at, one more thing I want to make. My comment is take this equation and I take the derivative of this. Suppose I take this expression and I do dp by dt, right? I take the derivative with respect to time. What you will find is, you will find this to be equal to d times del square p. I can write as a differential equation or as an explicit form. You can check the correctness of my statement by actually taking the derivative of this expression with the t. So this is normally you call diffusion equation. So the diffusion equation is exactly the same for describing the probability of a Brownian particle with this coefficient d, and that d is given by, again, kBt by z. That d is given by kBt by z, as I pointed out. That d is kBt by z. Okay, so what are we going to do this? The question, it's obvious. If I can measure this mean square displacement by some means as a function of time, then I will know what d is. And d is temperature divided by friction coefficient. I know the temperature. So if I have some expression for zeta, then I can use that information to characterize this particular object. Okay, let's do that. So the d turns out to be equal to, right? D is equal to kBt by zeta. This is Einstein. And for a Brownian particle, the particle which is swimming around or moving around in a solvent, Stokes had a calculation to show that zeta is equal to 6 pi viscosity of the solvent times particle radius. Remember, my particle has a radius r, and the viscosity of the solvent where it is moving around is viscosity, as I mentioned in the last lecture. So the radius and the viscosity, not the mass, okay? They dictate the friction coefficient according to Stokes, exact calculation. Therefore, we combine them. So d is equal to, combining them, d is equal to kBt over 6 pi eta naught r. This is called a Stokes-Einstein. Stokes-Einstein. Therefore, if you measure D either by microscopy, right? Either by microscopy, that is making particle tracking. You do particle tracking, you can put fluorescent tag, whatever. Well, however you do this, by particle tracking, you measure D. Then you will be able to, if you know the viscosity of the medium, you'll be able to say something about size of the particle. This is a very general result. Another way to measure D is using dynamic light scattering. Okay. Another way is a dynamic light scattering. And how do you do this? Okay. And I already introduced this, right? You have a sample here, polymer object, incident beam comes in, and then you have scattering angle theta, and then you measure the intensity, and the scattering wave vector k is equal to 4 pi over lambda sine theta by 2. We went through this again and again, right, in the early part of the course, right? So you measure I scatter intensity at some wave vector k at some time t. And then you measure at an earlier time, I, same angle at an earlier time, right? And of course, when you make measurements, you make a measurements for a fixed time delay many times, and then you average it out. And that's what your instrument tells you. Scatter intensity at some wave vector, some angle k, given a particular incident beam, and at the earlier time, and you measure this experimentally. Theoretically, this is related to dynamic structure factor. This is dynamic structure factor. Okay, and that dynamic structure factor is, you can derive it, and that looks like this. And I'm sure you already know this. S of kt is equal to S when at 0 time. Oops, sorry. Oops, sorry. K at 0 time. Then I have an average, right? That is e to the, say, ik, or you can have any sign you want, plus or minus ik dot the position of the particle at some time t minus position of the particle at an earlier time. For this, the Brownian particle. When t is equal to 0, then R0 minus R0 is 0, e to 0 is 1. So you have t is equal to 0 correlation function, that's the equilibrium correlation function, which we know how to do, Wurms and Zenica, all the things, the Zim plot, all those things we did before. But the dynamic part, that's the way it turns out. So the way I will do this is, I will average over this probability distribution function. I have already given that probability distribution function, and using that probability distribution function, I'll perform this average. If I do this, what I get is this is equal to yes, k0 e to the minus k square over 6 r of t minus r of 0 square average. It turns out to be a very neat result. E to the minus k square over 6 times this mean square displacement of the particle. And we have an expression for this. Mean square displacement of this is given here. I already gave you here, right? That is that quantity. So I substitute that back. So therefore, this is equal to S of k0 e to the minus k square over 6. Then the usual thing, right? 6 kt by zeta t minus m over zeta 1 minus e to the minus zeta over m t. I think that's good enough. Okay, that's my full expression. So you need to be careful as an experimentalist or even as a simulator. You have to be very careful that the exact result is this one. Right? Only if, only if, okay, only if a t is larger than tau, then whole thing turns out to be 6 dt, as I pointed out in here. I'm emphasizing. So only if this is true, the mean square displacement goes like 6 dt. So under those circumstances, if that is true, then if that is true, then this is equal to s of k 0 e to the minus d k square t. Right? Kt by zeta is d, 6 cancels out, d k square t. These things go away. Therefore, if I plot, for example, s of k t divided by s of k0, that would be e to the minus d k square t. Let me rewrite this. Since it's a t, the prefactor should be a rate. That's 1 over time, right? I'm going to rewrite this to be minus gamma t. Gamma is rate, but that depends upon k. So gamma k. So this is rate of decay, rate. Right? Therefore, if I plot logarithm of s of kt divided by s of k0, then what will happen is, right? You'll have something like, right? How do I take the logarithm of this? You'll have a result like this as a function of t. It's exponential, right? And that gives me, right? That gives me a slope, which is the rate, gamma k. Right? Logarithm of this is simply, right? Logarithm of that is simply gamma kt. I take this logarithm of this, logarithm of exponential of this, simply minus gamma kt. Right? And at t is equal to 0, right? At t is equal to 0, this quantity is 1. Right? So this is going to decay like this, minus gamma k. And then what I do is, what is gamma k? Gamma k is as a function of k squared, because gamma k is equal to dk squared. Okay, so you should be a straight line. You should get a data points like this, right? And you have to make sure those data points must be going to the origin. If you draw conclusions based upon this, right, it should go to the origin, because the gamma k is perfectly proportional to k squared. When k is equal to 0, gamma k must be 0. But you cannot make a measurement for k is equal to 0, because that's a 0 angle. You can't do that, right? Therefore, you have to extrapolate, but the extrapolation should go through the origin. And then the slope of this gives me, obviously, d, diffusion coefficient. This is another way to measure the diffusion coefficient. Okay? This is actually bread and butter for polymer physicists and polymer people who are interested in characterizing the polymer that they made, because you want to know the size. Once you know d, right, you know the radius of the particle, size of the particle. Okay, so that's the basis of this is this expression. Basis of our argument is this expression, which came from solving our Langevin equation. And the reason I'm going through in great detail for the Brownian particle is the conclusions we are drawing are very general, they're universal. We'll be able to implement the same conclusions for branched polymers, polyelectrolytes, you know, any colloidal particles, aggregates, soot particles, aggregate of soot particles, and things like that. In general, this is true. Now, what I like to do is I like to share with you some experimental data of how experimentalists actually play with this game. Right? So let me go back to the handout that I gave you. Give a handout. Okay, so here is a paper. These are latex spheres, polystyrene latex spheres. The radius is a 0.3 micron. The references are given in here. And this is a logarithmic plot, right? Semi-log, right? So S of kt divided by S of k0, as I pointed out, as a function of t, right? As a function of t, it should be a straight line, right? And that's what you see, right? Right? This slope gives me gamma k. The slope gives me gamma k. Then what I do is I take that gamma k, get the slope here, and I plot for a one particle. This is now a different system. Here the radius is 0.172 micron. I plot this gamma k as a function of k squared. Please notice this. This is a very beautiful straight line, right? Beautiful straight line. Okay, and therefore from here you can get diffusion coefficient. Then what happens is, suppose I take a different system, and the radius is even smaller, 0.043 micron. Right? Suppose I take a particle smaller. Again, I get a straight line going through the origin, and the diffusion coefficient here, the slope is larger, diffusion coefficient is larger. And we know that from Stokes' Einstein law, right? The d is 1 over r, kt by 6 pi eta naught, r is radius. When r is small, the diffusion coefficient is larger. And if you get those values, right, and they're exactly what you would get, what you should get from other measurements by optical microscopy. These are all, calibrating samples, right? You get exactly the same answer. Okay? So that's the way we do. We do make measurements and then capitalize on the measurements, interpret the size. Now, let me tease with you with a question. Suppose one of your colleagues comes and tells you, some distinguished professor comes and tells you, right, whom you have tremendous amount of respect. He comes and tells you, oh, I measure Stokes Einstein d going like kt by 6 pi eta naught r, and I find r depends on k, depends on the scattering angle k, scattering wave vector k, right? And what would you tell your distinguished professor? You have to tell the professor, no, this cannot be right. Because that means, right, if a gamma k went like k squared, okay, that means this means dk squared. That means d is independent of k. Independent of k. If d is independent of k, d is equal to kt by 6 pi eta naught r. T doesn't depend upon k, eta naught does not depend upon k. R is independent of k. It must be. Suppose let's work backwards. If r depends on k, the professor tells you r depends on k, that means d depends on k. If d depends on k, gamma k is not k squared. Gamma k is not, this means this is not true. This means gamma k depends on k power something else. So what you do is you ask the professor, please go and check this plot gamma k versus k squared, see whether you really get a straight line going through the origin. Because if that happens, there is no way you can have r depending on k. It's impossible. So these are the checks and balances you have to do. So you really have to make sure when you interpret your data, simulation, experiments, it doesn't matter, you have to make sure you get this one. Without making sure this is true, the value you get for r may not be correct. So you have to make measurements at multiple angles and make sure this rate is proportional to k. So only then you can say something about r. Otherwise, you make a measurement, right? Go to the lab, you have some standard instrument, you make a measurement of one angle, and the one angle will give you r. That doesn't mean that it's really in the diffusive regime. Okay? So that's what I want to warn you in terms of interpreting the data. Okay. And I think we have 5 more minutes. And I'd like to bring up one important comment. The important comment is the following. Remember, we talked about this particle, right, with the radius r, m, undergoing Brownian motion. right? Undergoing Brownian motion. That's what we talked about so far. In a medium of solvent, which has a viscosity. Due to the presence of this particle, right? Due to the presence of this particle, where there is also friction coefficient, we talked about friction coefficient. Due to the presence of this, viscosity of the solution also changes. And again, the credit goes to this gentleman. And what he showed was the change in viscosity of the solution suspension with respect to the solvent viscosity divided by solvent viscosity. That's equal to, he calculated this to be 5/2. The calculation is not a simple calculation. Obviously, it took this person to do it. 5/2 for the first time. Number of particles in volume V. This is number of particles. In volume V, this is V, volume of the box for your solution, times the volume of a particle, 4/3 pi r cubed. That's the volume of the particle, number of particles divided by volume. So this is, we write this to be 5/2 phi. This is a volume fraction of the particles. And V is volume. Okay. So this is a beautiful calculation, it turns out, and we are going to be using this equation and this equation. Both of them come from Einstein. We will be using this equation, right? This equation. We'll be using this equation and this equation again and again when we talk about polymer dynamics. When we talk about the first equation, mean square displacement, we are looking at one chain. Here we are looking at the whole system, from microscopic to macroscopic description of polymer solutions. We'll be using these fundamental equations conceptually. And the mathematical details are specific to the system, but in general, we'll be using the concepts extensively. And at this point, I think I want to stop sharing